We live in a contaminated world. Some of this contamination, such as smog and smoke, can be seen. Much of it, however, is invisible. This smoke floating in the air is actually composed of thousands of particles which are invisible to the unaided eye, but which can be seen when concentrated into a cloud. Almost every item we deal with in our daily lives produces contamination. This report, for example, is typical of the paperwork of industry. Minute particles slough from its pages, becoming visible when viewed in strong crosslight. Our clothing, too, is a source of lint and dust. The normal processes of skin growth make our bodies a source of airborne particles. For example, the cleanest head is continually scaling tiny pieces of skin. And a clean pocket handkerchief carries its share of airborne contamination. Yes, our contaminated world is getting dirtier each year as population increases and our planet becomes more industrialized. The factories which supply man's needs are contributing their share to the contamination which surrounds us. The smoke rising in this room symbolizes the increasing airborne contamination in the world. Control of such dirt and contamination is the subject of this film. Our technology demands precise devices made of intricate parts, designed for exact fit with each other. But such precision fit is difficult if any foreign particles become lodged between close-fitting parts. With alignment of parts measured in 10,000ths or even millionths of an inch, a particle as small as a micron in size can cause the failure or malfunction of a precision device. A micron is a unit of length equal to 1,000th of a millimeter or 40 millionths of an inch. A human hair measures about 100 microns in diameter. The smallest particle visible to the unaided eye has a diameter of about 10 microns, as illustrated by fine dust, a red blood cell, or a droplet of fog. Particles as small as 0.3 of 1 micron can cause production problems. A 0.3 micron particle, for example, is the largest of the filterable viruses, or the average particle of tobacco smoke. Eliminating such minute particles from the air continues to be a major industrial problem. To combat contamination problems, industry uses clean rooms in an effort to supply dust-free environments. The supply air for clean rooms enters through filters which trap airborne particles, and additional precautions are taken to prevent dirt being brought into the room by the workers themselves. Mechanical shoe cleaners are used to stop contamination from coming in on the workers' shoes. Clean room workers are required to wear special lint-free clothing while in the clean room. In spite of these precautions, however, the older conventional clean rooms have not proven completely adequate for manufacturing components for the space age. The reasons for the limited success of conventional clean rooms are shown in this simplified drawing. The pattern of airflow within standard clean rooms is almost random, resulting in turbulence and dead air pockets. Contamination is inevitably produced within the room, and the turbulent air floats the lighter particles about. Since these rooms have practically no self-clean down capability, particles may circulate many times throughout the room. They tend to be attracted to each other as they drift, becoming larger and having several chances to contaminate the work in progress. In order to provide improved clean room facilities, Sandia Corporation of Albuquerque, New Mexico, has developed laminar airflow clean room systems. Essential elements are a blower, a plenum chamber, a highly efficient filter bank equal in size to the cross-section of the room, and walls to confine the moving air. The system is self-cleaning, since large air volumes sweep uniformly through the area, removing airborne contamination. The air flows from ceiling filters to the floor, from one side wall to the opposite wall, or from one wall to the floor. Airborne particles are removed almost instantly by the airstream. The first successful laminar flow clean facility, developed in the laboratories of Sandia Corporation, uses a wall-to-floor air pattern. The room provides clean working conditions at the workbench and tends to clean the air throughout the room. This type of laminar flow is applicable to production facilities where a large number of operations are done at fixed workbenches. The clean bench was developed from the first laminar flow room and is now in wide use due to its portability, low cost, and efficiency. It can be moved to any area where needed, since it requires only electric power for its operation. The bench supplies clean working conditions within seconds after being turned on, and operations within the benchtop enclosure are not affected by dirty operations which may be going on nearby. The clean bench also lends itself to production line operations, since benches can be placed side by side to make up production lines of the required length. Laminar airflow principles have been applied in this large cross-flow clean room. Operations requiring critical cleanliness levels are performed closest to the incoming filtered air. Operations which may have less demanding cleanliness levels or which introduce airborne particles into the room are placed downstream from the first work location. The airflow of cross-flow clean rooms allows even paperwork to be performed safely in the room, since the particles produced from erasures and from handling paper are removed from the room within seconds after being generated. Such particle-producing work is naturally done closest to the exhaust end of the room. In the downflow room, the entire ceiling of the room is a high-efficiency filter bank. Clean air enters through the filters, passes straight down through the room, and out through floor gratings. This airflow pattern takes advantage of the natural settling of particles due to gravity. The downflow air movement removes contaminating particles from each work area as soon as they are produced. Dust and dirt cannot drift about, and each work location is thereby isolated from the others. A variety of operations can thus be performed in the downflow room without cross-contamination. On a smaller scale, the airflow pattern of the downflow room is utilized in this downflow fume hood. It is used where the work produces toxic or contaminating byproducts which must be removed. The clean air flows through the hood and is exhausted to the outside air after treatment to remove contaminants. Another downflow application is this portable curtain-type unit for use with large items requiring clean atmosphere for assembly or checkout. Maintaining the high standards of cleanliness of other laminar flow devices It can be used with items too bulky or too heavy to be taken to a clean room facility. Research and development activities, which previously had been severely limited, can now be accomplished with the availability of completely clean atmospheres. For example, research engineers are studying the interaction between the surface of a substrate and thin films, which are evaporated onto its surface. Advanced applications in this field require the deposition of very closely spaced fine lines with dimensions the thickness of a human hair. A dust particle is intolerable because it would interfere with the deposition process or cause an electrical short across the narrow grooves. By mounting both the cleaning devices and the vacuum system in the clean area, the necessary cleanliness is achieved. Clean environments are helping in the development of this electrically controlled timing device. A moving gap in an enclosed column of mercury provides a timing action. Varying the current flow regulates the speed of the moving gap. Small quantities of mercury are introduced into the tiny capillary tubes, measuring only 15 thousandths of an inch in diameter. Proper operation of the device depends upon cleanliness of the assembly. By filling and sealing the tubes within the clean bench, the cleanliness required for proper operation is assured. The clean atmosphere of laminar flow devices is also being used in developmental studies of microcircuitry. The substrate, or base, upon which extremely thin metallic films are deposited, must be clean in order for the circuits to perform as designed. Any foreign material on the substrate at the time of plating makes circuit evaluation difficult or erroneous. For example, dust specks on the substrate will cause pinholes. The medical profession is showing increasing interest in application of laminar airflow to medical and surgical problems. The Loveless Foundation for Medical Education and Research, Albuquerque, New Mexico, is studying the possibilities for using clean rooms in medical practice, in improving the environment for the care of any infant who might be more susceptible to infection, in reducing the likelihood of infection of any burned patient, in providing a sterile environment for the handling and preparation of tissue cultures. Research in this area is hindered by contamination, which appears in culture specimens, making them worthless for further study. Doctors are also planning to adapt laminar airflow to operating rooms in an effort to study the role of airborne bacteria in post-operative infections. Similar operations will be performed on laboratory animals in both standard and laminar flow operating rooms to determine if laminar flow conditions will further reduce the risks of surgery. Further investigation of medical applications of laminar flow clean rooms is anticipated in allergic and infectious disease control, in more highly controlled sterile supply handling, and in supplying the optimum environment for all infants in hospital nurseries. The planet Earth will be an increasingly contaminated globe for many years, as man's machines and man's civilizations spew forth wastes. But in spite of the dirt and contamination in the world, clean work must go on in the hospitals, in the research laboratories, in the development shops, and in the production plants of the nation. Laminar flow clean facilities will help make precise, immaculate work possible in this contaminated world. With the right facilities, clean air is a breeze. The laminar flow systems seen in this film have been developed by Sandia Corporation, contractor to the United States Atomic Energy Commission. Further information on patent applications pending is obtainable from the Assistant General Counsel for Patents United States Atomic Energy Commission, Washington, D.C., 20545. Federal Standard number 209 is available for standardization of definitions and levels of environmental control. Copies are available from General Services Administration, Business Service Center, Washington, D.C., 20407.
Lay down.